Fantastic.
Okay, so anything going in now from so he can't
Yeah, I can hear you now. Somebody's talking. So the questions afterwards,
yes.
I'm plugged in, I can view the live feed in my web browser. So if I stop sharing my screen, I may be able to hit questions directly using that system and be able to respond immediately rather than you having to repeat them.
Well, either way.
Okay. Yep.
I'll let you finish the call. Okay. I'm assuming you can stand on this.
I'll finish the thanks.
All right. Okay, well, thanks very much, everybody, for coming along tonight. It's huge turnout. Brilliant. Thanks for supporting the group and coming to learn more, hopefully. We've got a real treat tonight, and I'll come on to who's speaking in a second. I just wanted to touch on a couple of things. Firstly, the first is, for the first time, we have sponsorship for the group, which is absolutely fantastic. Deloitte Digital have put their hands in the pockets and have helped us with the event hire, the room hire, and also are paying for the drinks. We had a slight issue with drinks. Jonathan is sitting over there trying to keep a low profile in the back, but you can say thank you to him afterwards. So hopefully that's the beginning of an ongoing relationship there with regards to the support of the meetup, which is awesome. There was a bit of an issue with the beer. It all ended up being delivered at the wrong place, so we haven't quite got as much on the right side, but we shall get through that. So a couple of things just to touch on. The group's on Twitter, Blockchain Scott. There's a hashtag Blockchain Scott, imaginatively as well this evening. If you're not in the meetup group, please sign in, join the meetup group. It's simply type meetup.com and type in Scottish Blockchain Meetup. And that's pretty much it in terms of housekeeping. The toilets, if anybody needs them, are straight out that door, straight through the door that way. So on to tonight. Tonight, it's been a busy month since the last time we all met in here. We've had a lot of things happening. As usual, I'm not going to say anything apart from a couple of things which include, well, the DAO was going to take over the world the last time, and then it got hacked. So there's a big question around smart contracts. There's all sorts of things around forks and Ethereum. There's lots of people in this room who know a lot about that. Certainly our speaker tonight knows a lot about this subject as well. We've got the halvening. We've got the halving of the Bitcoin block rewards, I believe scheduled for Saturday. So this is the first time for 4 years that miners are going to see half the rewards coming in. We've got Hillary Clinton saying in her campaign at the moment that she's all behind blockchain technology. So that's good, isn't it? And we have all sorts of other exciting things. Microsoft's coming out with a Fabric platform. There's too much to mention. I just want to say that because I think at the start of each meetup, let's have a few discussion points and pick up on some of these things because we do have some experts in the room. I don't count myself as one, but there are some here. So, on to this evening. We are extremely lucky and privileged to be joined tonight. I'm kind of standing slightly in front, and I'm just going to check that you can see the audience, but by Dr. Gideon Greenspan. I met Gideon, I just realised Gideon can't see me, but I met Gideon probably, I don't know, at a conference in London about a year and a half ago, something like that. So Gideon was talking about his business at the time, MultiChain, and gave an incredibly good talk. Since that time, as some of you, many of you in the room will know, he has blogged quite extensively in detail about lots of different aspects of blockchain technology. Probably one of the best blogs you'll read. I'm sure you won't mind me saying that. It's incredibly perceptive and analytical and everything else. It pulls it together, but in a very easy to understand way. I'm going to read out his bio because I think it's interesting. So Dr. Gideon Greenspan is the founder and CEO of Coinsciences Limited, the company behind MultiChain, the popular platform for private blockchains. MultiChain includes features such as permission management, native asset support and simple configuration and deployment, and has been used successfully for blockchain pilots in some of the world's largest banks, consulting firms, financial technology and IT companies. And Gideon's, as I said, a very interesting individual, well-known writer on private blockchains, with a reputation for going beyond the hype to focus on genuine and practical applications of the technology. You've got a very interesting background. In terms of other businesses, you've got BA and PhD, I feel like I'm on This Is Your Life, BA and PhD in computer science from Cambridge and MA in philosophy from London. He teaches software entrepreneurship at 2 universities in his hometown of Tel Aviv, where, are you in Tel Aviv at the moment, Gideon?
Yes, I am.
Yes. So he's joining us from Israel at the moment. And I remember reading something, actually, Gideon, where I think you likened Ethereum to asking a toddler to cook you dinner or something similar in one of your blog posts. So not to be provocative, but I think that's the sort of insight that I would like to hear more about. So I'll pass across to you.
Thank you. So can you guys all hear me okay? Yeah, hi, so it's a pleasure to be with you remotely. I actually have more connections with Scotland than you might think. I was born in Glasgow, and then my family moved elsewhere when I was quite young, and I spent many a happy August in Edinburgh for the Fringe Festival my younger days, so I visited many times. So thank you very much for coming. We're going to talk this evening about private blockchains. In my view, a much misunderstood subject and somewhat controversial subject for some. As I mentioned, I gave a similar talk in London. For those of you who object strongly to the idea of private blockchains and have tomatoes hiding under your chairs ready to throw at the screen, save them for the end, because I'm going to be throwing quite a few tomatoes at myself during this talk. But hopefully we can kind of separate the myth from the reality and get some kind of deeper understanding of what people are talking about. So let's get started. So if we want to kind of make a very simple history of blockchains in terms of the way that the media has seen it, everything started in 2009 with Bitcoin. Actually, the media didn't pay a great deal of attention to Bitcoin for the first few years, but that's when Bitcoin started off. And then a whole bunch of people noticed that inventing a cryptocurrency was a very, very good way to get rich. And therefore, kind of a couple of years later, we had a whole bunch of other cryptocurrencies that came out, some of which were very straightforward forks of Bitcoin with small variations like Litecoin, and others like Next and Ripple were kind of new systems written from scratch. And there was a lot of creativity and activity in that area for kind of the 3 years between 2011 and 2013, at which point I think people kind of got tired of altcoins and kind of stopped, although we see now a resurgence with Ethereum. And then kind of last year, the conversation seemed to shift a bit with the idea of a private blockchain or a permissioned blockchain. The financial world started to pay attention to what Bitcoin does and how it does it, and thinking about whether it could do similar sorts of things in a way which suited it. And then we released our product just a little bit over a year ago, the first version of our product. There have been other people, 1 or 2 people active beforehand, and now in the last year we've seen a huge amount of activity in this area around the notion of kind of cherry-picking many but not all of the elements of cryptocurrencies to create some kind of system which works a bit like them and a bit differently for them for kind of enterprise purposes. So to start off with kind of understanding why people are doing this, it helps to think about what a public blockchain like Bitcoin or Ethereum is, and how that looks from the perspective of an enterprise or a serious company. And this is something that we discovered actually in our own painful way, because we started our company developing something, a technology on the Bitcoin blockchain. And when we started talking to serious companies about this stuff, we learned about a huge range of issues that these public blockchains present to enterprises today. And I want to stress today because I think it may well be different in 10 years' time. And there's an interesting comparison you can do with the internet and how at the beginning it was something that big companies wouldn't touch, and now, of course, everyone uses it. But today there's a whole bunch of reasons why public blockchains aren't something which is suitable for large companies to work with. And there's a number of reasons why. So they have very low capacity. Bitcoin is a few 100,000 transactions a day, and there's segregated witness and other ways to increase that, but it's not increasing rapidly anytime soon. The governance structures of these cryptocurrencies is problematic. So when I gave this talk in London about a month ago, I talked about the proven difficulties of governance in Bitcoin in terms of the block size debate and all the mud that's been slung around that. And I kind of said, well, Ethereum is actually presenting a different example about maybe how governance is handled correctly. But now we see with the DAO and all of the problems that that's had and all the debates about whether to fork and how to fork, that there are governance issues in Ethereum as well. And it may just be that a public cryptocurrency is something which is very difficult to govern in a very straightforward and reliable way because of its nature. Costs are unknown in terms of transacting. So the cost of transacting on something like the Bitcoin network will depend on the network's transaction fees at some time in the future, and also what the value of a Bitcoin is. So no one quite knows what those things will be. The idea that we are dependent on anonymous miners to validate transactions, especially in jurisdictions which are not comfortable from a Western perspective, is something that makes public blockchains unusable for many enterprise purposes. The notion of a cryptocurrency itself is obviously problematic for at least financial institutions to touch. If you look at a public blockchain, anybody can write to it, and even worse, everything that's on it can be seen by everybody in the world. And this is also something that's not so comfortable for many enterprise applications. And to kind of summarize, what we have is a kind of a single bloated ledger. So we have a single ledger which the entire world is meant to use for all sorts of different purposes. And that's a very powerful thing, but it also leads to a huge amount of information in this ledger, which isn't necessarily of interest to particular companies that want to use this type of technology. So putting all these things together, the conclusion that we came to, and obviously many others came to, is that if you're looking at enterprise applications of blockchains, they're not going to be on public blockchains today. And as I said before, you can revisit that in 5 years or more likely 10 years, and maybe the picture will change. So what does a blockchain for an enterprise look like? Well, my view about this is that it's actually should be viewed as a type of database. Specifically, it's a database which is shared between multiple companies, or another way of saying it is a database which is shared across trust boundaries. And that makes it different from most databases, and we'll go into this in a bit more detail in a bit. But even though it's shared between multiple companies, it's still private in the sense that it's not visible to the whole world. Another important feature of enterprise blockchains is Byzantine fault tolerance. That means that the system can survive one or a few nodes behaving maliciously or malfunctioning or dropping off the network or anything else. In other words, there's no way for one participant or a small number of participants in this chain to mess up the system for everybody else, either by mistake or on purpose. Companies like to have control over the capacity of these systems, and they want to know what it's going to cost as well, so it's controlled in a way that public blockchains are not. Mining is a bit of a misnomer, but nonetheless, the entities which validate transactions are designated for that purpose rather than this being something which anybody in the world can do. These enterprise blockchains don't have a cryptocurrency. They're nothing to do with cryptocurrencies. They don't deal in that asset class at all. They're administered collectively between multiple parties or multiple companies. And kind of to summarize the difference here, what we're talking about really is blockchain as a tool. It's simply another tool in the IT toolbox of large companies, in the same way as database platforms are a tool and messaging platforms are a tool. And really this has nothing to do with ideology and nothing to do with trying to transform the financial system or trying to transform society. It's simply a new, efficient way for companies to interact with each other, which enables them to do some useful things. And that may be not very interesting for many people in the room, which I can understand and respect, but that is quite interesting to many companies who spend a lot of money on IT and are looking for ways to make their IT more efficient. So this is the first tomato that I'm going to raise. And the first tomato is the claim that if you look at a permissioned blockchain, as opposed to a public blockchain and a cryptocurrency, this is actually just a shared database. Now, I actually agree with this sentence, apart from the word just. So it is a shared database. I think that's an accurate characterization, but I don't think it's just a shared database. And I don't think it's just one because I think it's a new type of sharing a database, a new way of sharing a database, which doesn't match what we generally do today. So this is the way in which databases are generally shared today. You have a server, and it could be multiple servers. It could be some kind of distributed group of servers, but still it's under the control of a single entity. One company or one entity is in charge of this server or this group of servers. The application logic, which I'm denoting with those squiggly brackets, sits on this server, and the server as well communicates with a data store on disk. It reads from that data store on disk and it writes to that data store on disk. Now, anybody who wants to use this database, and there's going to be multiple users of this database, so it is shared, if they want to gain access to that data and modify that data, they have to do it by going through this central entity. So we've got a client on the right, it has some way of authenticating itself. It can be a shared key or something else. It sends a request to this centralized system. The centralized system then examines the request, applies its application logic, decides if it likes the request or doesn't like the request, checks if the request is authenticated, performs the necessary operations on the database, and then sends a response back to the client over the same communications channel. So this is a way in which a single database can be shared, and it's a way in which many, many databases are shared today. But the way in which they're shared is that they're ultimately under the control of a single entity, which decides who can connect, what kind of application logic runs, and what kind of modifications can be done to this database. And that's a common way, that's a common pattern that we have in database architecture today. When we talk about a blockchain, what we're actually talking about is something which enables a peer-to-peer shared database. And it looks a bit different. So we have here in the picture 4 nodes. Each of these nodes sits under the control of a different entity. Each node contains a full copy of the database's current state. Each node contains a full copy of the application logic, although that logic is expressed slightly differently. It's nonetheless application logic. And these nodes communicate with each other in a peer-to-peer fashion. So no individual node is in charge. Transactions are generated by a node. They're signed using that node's private key to prove their origin. The transactions travel between the nodes in a peer-to-peer way. And then transactions also get grouped together into blocks, which also travel between the nodes in a peer-to-peer way. Blocks represent a set of transactions which are being confirmed or which are being validated. So it is also a shared database, because ultimately we want the database in each of these nodes to be the same. But the method of sharing is very different. Rather than somebody being in charge or a single entity being in charge, everybody is an equal peer here, and no single entity gets to decide who gets to do what. It's something which is agreed upon by a matter of consensus. And so in this type of database, the blockchain actually is the method of creating consensus. So if you want to actually describe one of these systems, although they are called blockchains, I think maybe a more accurate way to describe it is a peer-to-peer database which is empowered or enabled by a blockchain. And the job of the blockchain is to create consensus between the nodes. In other words, to make sure that even if some transactions conflict with other transactions, or even if certain nodes drop off the network for a while, or even if some node is booting up somewhere in the middle of the, when the system's already been running for a while, the blockchain is essentially the mechanism of ensuring that all of the nodes come to agreement on what the content of the database is. And the blockchain is simply a log of transactions. And that's exactly, if you look at a public blockchain, that's exactly what it is. A public blockchain is simply an ordered log of transactions, with a bunch of stuff added onto it in order to make it immutable and so on and so forth. But the main content of a blockchain is simply a log of transactions, which is created as a matter of consensus and which is applied by all of the nodes to make sure that they agree on the content of the database. So if you look at the requirements of a peer-to-peer database, a number of things kind of drop out of this if we're going to share a database in this way. First of all, we need to have some kind of notion of a transaction being atomic, like in any database. But here, this atomic transaction, atomic means that the entire transaction succeeds or fails as a whole. And that's something which is common to all databases. But here, the atomic transaction is actually sent over the network as a transaction. So in traditional types of shared databases, we don't have this notion of a single packet containing a whole transaction. You can have multiple queries that are part of a transaction being sent in individual packets. But here we have the notion of a transaction travels over the network as a packet, as a whole, between nodes, and is either processed as a whole, if it's valid, or not processed as a whole if it's not valid. So that's one characteristic that we need. The next characteristic is that if we're having a peer-to-peer database, what that means is when you look at a transaction from the perspective of a specific node, you've got no idea where that transaction came from. You may know the node that sent it to you immediately. In other words, you may know which of your peers transmitted that transaction to you, but that doesn't say anything about the transaction's origin, where it actually originated in the network. So we need some way of knowing the origin of a transaction, which enables a node to assess that origin and confirm that origin, but without being able to fake other transactions to come from that same origin. And that means we need to use something which is called asymmetric cryptography or public-private key cryptography, which is now a very common technology and applied in all sorts of ways. Every transaction is digitally signed by the entity which creates it, and that proves the transaction's origin. And the flip side of that is if we want to have transactions using public-private key cryptography, we need to tag data in the database with public keys. In other words, each piece of data in the database has an associated identity, a public identity, which essentially says who is allowed to modify, who is allowed to touch this piece of data. And that's exactly, if you look at something like the Bitcoin protocol, what you actually have in the output of a Bitcoin transaction is a piece of data, which is the quantity of Bitcoin, and you have a public key, or there's more complicated versions, there's multi-sig and so on, but you have some kind of public identifier which says who is allowed to modify, who is allowed to touch this piece of data. And the act of spending some coin in the Bitcoin protocol is actually the act of modifying that piece of data and actually deleting it and sending its value to some other rows in the database. So we need this public-private key cryptography if we're going to have a peer-to-peer database. The next thing we need is, if we're going to have this database written to by multiple parties who don't necessarily trust each other, then what we actually have is a shared write database. We have a database that multiple people can write to directly, even though they don't trust each other. And if we're going to have a shared write database, we need to have some kind of way of expressing the rules about what is a valid transaction. And that's something that I call a transaction constraint. In other words, if we have a database which represents, for example, a financial ledger, and I have £10 in this financial ledger, and I send a transaction which spends my £10 and sends £15 to someone else, well, that can't be allowed by the system, right? Because we can't allow people to conduct transactions which create money out of thin air, unless, in the case of Bitcoin, they're miners who actually are permitted to do that. So we need a way of expressing constraints on what is a valid transaction. And that is a different type of constraint to the common type of constraints you see in regular databases today. Regular databases today have all different types of constraints about what can appear in a column, rules about certain rows. They have something called foreign keys, which map between the entries in one table to another table. But this notion of defining a constraint on the level of a transaction as a whole is certainly not a common paradigm in centralized databases. I haven't seen it in any of these databases, but it may exist in some platforms I'm not aware of. But certainly it's not a common way of defining the rules of a database. Because this isn't a problem if the database isn't being directly written to by people that don't trust each other. But a blockchain is that type of system, therefore we need a way of expressing transaction constraints. And there are various ways of doing this, and we'll talk in a minute about kind of the two common paradigms, one of which is the Bitcoin paradigm and one of which is the Ethereum paradigm. And the last thing is, as we discussed before, we need some kind of consensus mechanism. So if it's a peer-to-peer database and there's no individual node which is in charge, we need some way of ensuring that all of the nodes come to consensus, even if it's a delay of a few seconds or in public blockchains longer. We need a way to ensure that all the nodes ultimately come to consensus, because there's no meaning to the sense of a shared database if different nodes have different opinions about what that database contains. And so we need to make sure that they all come to agreement about that. So there's a whole bunch of requirements there. And these requirements are kind of direct consequences of the notion of directly sharing a database. And these requirements are not answered by traditional centralized database platforms. These requirements are something which we see in blockchains. So let's just have a look at an example of a transaction constraint. So this is a Bitcoin type of constraint. And I say a Bitcoin type because this is a multi-currency Bitcoin style transaction, and it doesn't allow for transaction fees. But the basic transaction model is the same. So this is a transaction in which Alice and Bob have decided to exchange some funds. Alice had £10 in the system, Bob had $15 in the system, and well, post-Brexit I should probably update these numbers, but we'll stick with this for now. And then at the end of this transaction, Alice is going to have Bob's $15 and Bob is going to have Alice's £10. So they've conducted a safe atomic exchange. Now there's actually some rules in these types of transactions. So first of all, a transaction, as I mentioned before, has to be signed by everybody whose funds are being spent by the transaction. In other words, there's no way that we can do a swap with Alice's funds or a swap with Bob's funds unless they've both signed off on the transaction to say that they agree to this swap. We can't force people to swap money. And the second thing is that the total quantity on the left per asset type is the same as the total quantity on the right per asset type. In other words, we have a rule in this type of transaction which says that you can't create or delete money by moving it around in the system. And actually the way to look at this transaction is a transaction which deletes two rows in a database and creates two rows in a database. So the two rows that are deleted are the ones on the left. Those would be the inputs of the transaction. These entries in the ledger, in the multi-currency ledger, are deleted by the transaction. And the entries on the right are deleted in the database. And the entries on the right are created in the database, all in a single transaction. And so the way to understand Bitcoin's type of transaction constraints is that these are expressed in terms of a rule which looks at the rows deleted by a transaction and the rows which are created by a transaction and says something about those sets of rows. So in this case, we have a rule which says the total amount of assets in the rows deleted is equal to the total amount of assets in the rows created. And that is a type of transaction constraint, which could be extended to all sorts of other ideas. But in a financial ledger, it's quite simple. You're just comparing the totals. And that's one way of expressing constraint on a transaction. And as I mentioned before, this is not something that we see in general purpose centralized database platforms. There's no way to express these rules to say, look at a transaction as a whole, what rows did it delete, what rows did it create, let's say something about that set as a whole. And maybe just to clarify, the act of modifying a row, which is something that often happens in centralized databases as well, is exactly equivalent to deleting that row and inserting the replacement row with a modification. So anything which modifies a row can be expressed in terms of deletion and creation. So that's one way of expressing a transaction constraint in a blockchain. Ethereum takes a very different philosophy to expressing transaction constraints. Ethereum says the following. It says that you're not allowed to modify the data in a particular sub-database, and that means the storage of a particular contract. No one's allowed to modify that data directly, apart from the code which belongs to the contract itself. In other words, the contract contains the code for modifying that data. You cannot run that code directly. What you can do is you can send the contract a message. It will then examine the message, see who the message is from, apply whatever other logic it wants to, and based on that logic, it may decide to modify its own internal database. And this is another way of expressing transaction constraints, to say that the database can only be modified by the code which is associated with it. And we see here a very simple example of an Ethereum, a small piece of an Ethereum smart contract. This is taken from the subcurrency example smart contract. We should just focus on the bold text. Even for those of you that don't read code, it's quite simple to parse. Somebody's requested to send some money to someone else. So we're checking, first of all, that the person has enough money, if the from value is greater than or equal to the value to be sent. If so, we're deducting from the sender the amount to be sent, and we're adding to the recipient the amount to be sent, and then return 1 means this was successful. And if that condition that we checked before wasn't true, then we return some kind of a response to say that the thing failed, that the transaction was unsuccessful. So this is a completely different paradigm for achieving the same result. And that same result is having transaction constraints, having rules about what kind of transactions can be performed on a database. And for those of you who are familiar with traditional databases, what you're actually looking at here is very similar to a stored procedure in a regular database. Stored procedures are pieces of code that sit in a database and which collect a series of operations together in terms of things that can be done to that database. But the difference with Ethereum is that the stored procedures are enforced. In other words, there's no way to modify the data other than going through the stored procedure. You have to go through the stored procedure, whereas generally speaking, in regular centralized databases, a stored procedure is there for convenience, but you also have the ability to modify the data directly if you want to. But apart from that, technically speaking, it's very similar in its nature to a stored procedure. So the way in which I would look at this really is that this is just a new type of database. And if you look at the world of databases, there are a number of categories which are, some of which are well-known, some of which are less well-known. So the best well-known category would be your traditional relational database, things like Oracle or MySQL or Postgres and SQL Server. There's many products in this category. And this type of database is still the lion's share of the database market today. Kind of nipping at its heels is what's called a NoSQL database. This is a database which gives up a lot of the conveniences and a lot of the model of the relational database, but in exchange for which you get remarkable scalability, which is hard to achieve with relational databases. So again, there's a whole bunch of products in this category, MongoDB, Cassandra, many others. And this type of database may be something like 5 or 10% of the database markets today. Then we have kind of more niche types of databases. We have in-memory databases, which perform extremely well, but store all of the data in memory, which obviously can be very expensive if you have a lot of data. We have databases which are focused on making search very efficient, like Elasticsearch and like Solr. We have databases which are called graph databases, which enable the relationships between entities to be expressed very succinctly and for all sorts of operations on those relationships to be done in a very efficient way, more efficient than relational databases. And I think we just need to add a box to this page, and that box would be peer-to-peer databases or shared databases, or if you want to call it a blockchain, you could call it a blockchain. This is simply another category of database. And what characterizes this category is that it's a database which can be directly shared across trust boundaries. And that's quite a mundane thing, but possibly quite a useful thing. And when we're talking about permissioned blockchains, I think that's what we're actually talking about. It is a new type of database. So I hope I've answered the first tomato, that this is more than simply a shared database, that this is something that is a little bit different to what we're used to thinking of in terms of shared databases. Second tomato that's often thrown at this idea of a private blockchain is that this is not immutable. So immutable means cannot be changed. So the idea is, for example, in a public blockchain, that because of proof of work and because of the computational cost of subverting the blockchain, once data goes in there, once a transaction goes in there, very quickly it becomes extremely expensive or impossible to modify or to retroactively rewind that piece of data or that transaction. And the tomato that's thrown at permission blockchains is that that property of immutability doesn't apply in the same way, that permission blockchains aren't immutable. So before I kind of respond directly to this tomato, I want to just explain an example of how mining works in private blockchains. And mining really is about validating transactions. I'm bringing an example here from our own product in terms of how MultiChain does it. There's other options as well, but they all kind of share certain characteristics. So first of all, in a private or permissioned blockchain, validation of transactions tends to be based on signatures. So a block generated by a miner or by a validator is digitally signed in exactly the same way that a transaction is digitally signed to prove its origin. So a block is digitally signed to prove who generated that block. We have rules about who's permitted to generate blocks. So if you look at something like Bitcoin, Bitcoin has a problem, which is that because anybody can mine a block, and anybody can mine a block under any identity because anyone can generate as many public-private key pairs as they like, it would be possible in Bitcoin, even if we had some kind of voting scheme based on IP addresses or based on Bitcoin addresses or something like that, it would be possible for a single entity to generate many different identities under the scheme and therefore seize control of the network consensus while looking like there are many different people, but in fact just being one person or one entity. And that problem is called an impersonation attack or a Sybil attack. It's exactly the same problem you have when you put up an online survey and you don't know if your 10,000 responses are all from one person or all from a genuine cross-section of the population. And so this notion of proof of work to make it computationally difficult and therefore financially costly to generate a block is an excellent way to solve that problem in a public blockchain. So we make it not just something that anybody can generate a block just by saying, here, this is who I am, but they actually have to do something which is expensive and difficult and costs genuine electricity, and burns coal or burns gas or whatever it is, to generate a block. And that's how we make it much harder for a single person or a small group of people to seize control of the network. Once we have a rule which says only miners who are permitted, who are on the whitelist, are able to sign blocks, are able to generate blocks, that whole problem falls away. Because you cannot have an impersonation attack. I cannot pretend to be someone else unless I have their private key. And I can generate a new private public key pair to generate a block under a new identity. But if that identity isn't on the whitelist, no one's going to accept my blocks. So as soon as you have permissioned mining or permissioned validation of transactions, you can get much simpler mining schemes which prevent centralized control of the consensus. So MultiChain uses something called mining diversity. Mining diversity is essentially a way of a simple rule of just saying, well, a blockchain is only valid if the people mining it are sufficiently diverse. So, for example, if we have 10 permitted miners, then at least 8 of them have to mine in rotation, otherwise it's not a valid chain. And once we have some rule like that, proof of work is simply not required. And I'll show you just an example of how mining diversity works. So let's say a block was generated by the green miner, then a block was generated by the blue miner, and of course everyone knows it's the blue miner because they've signed the block. Then a block's generated by the red miner, and then the green miner comes along and generates a new block. But the rules of the consensus rules of the network say that the green miner isn't allowed to generate the next block because it's too soon since the previous block that they generated. So even if the green miner were to try to generate that block, nobody would accept it. Purple miner would come along and generate its valid block, which would then be accepted by the network, and then the green miner might be allowed again because enough blocks have passed since the previous time that they've mined a block in the chain. So this is a very simple idea. It's a bit like a round-robin consensus scheme, but with some leniency to allow for non-functioning nodes. And as I mentioned, there's various other ways to do mining or validation in private chains. Some systems have multiple miners or multiple validators sign off in a single block rather than having the blocks validated or mined in rotation. But the idea is always the same. You have some kind of list of people who have permission to attach their stamp of approval to a block, and you have some kind of scheme to ensure that at least a majority of them or a significant minority of them are working together or mining in rotation or co-signing blocks to make sure that a small group cannot take control of the chain. So that's how it works in private chains, and it's very different to public blockchains. So to go back to the question of immutability, if you look at public blockchains, their immutability comes from the cost of mining blocks, the difficulty of mining blocks, and the fact that you have to solve this difficult computational problem. And if somebody were to possess 51% of the hashing power of the network, whoever that person was, they would be able to secretly mine a chain in private. Their chain would be longer over time than the chain of the rest of the network, because they have 51% of the total capacity. In other words, they have more hashing capacity than everyone else put together. And then they could mine that chain in private for 3 months, 6 months, or a year. And then when the time was right, they could transmit their chain to the network. The network's rules would say, well, this is a longer chain and it's a valid chain, so we have to accept it. And they could essentially retroactively rewrite history for the entire public Bitcoin blockchain. And this is technically feasible. Whether it will happen, I have my doubts, but it's something that's technically feasible. And therefore, it's a little bit simplistic to say that Bitcoin is immutable, because Bitcoin could be muted or mutated. It makes more sense to talk about the threat model. In other words, it's pretty immutable, but there's a possibility of someone undermining it and retroactively rewriting its history. And the question to ask is, what would be the characteristics of such an entity? And to take an example, China spends probably on the order of $5 to $10 billion a year on the Great Wall of China, which is something like 1 million employees whose job it is to monitor and censor the internet content which is going in and going out of China. So they spend something like $5 to $10 billion a year on this system. And if China were to decide that public blockchains were a nuisance, and Bitcoin is a nuisance, and there's some possibility they will decide that because it is enabling Chinese people to circumvent capital controls, they could take what would be a relatively small part of that budget, use it to buy or to build a whole bunch of ASICs, secretly mine the Bitcoin blockchain in private, and at some time of their choosing, they could transmit their chain to the network and undermine the whole thing and destroy Bitcoin very, very quickly. So in terms of someone rich, like a government, and obviously the US government and other governments have a capacity to do this as well, it's not beyond the capacity today, if they chose to and decided it was important, to completely destroy public blockchains by having more hashing capacity than the rest of the network put together. It's not something which is that expensive to achieve. It's expensive, it's on the order of, say, $1 billion for Bitcoin, but it's not impossible to achieve. Now, if you look at private blockchains, well, they're not secured by hashing power. They're secured by distributed consensus, as I mentioned before. They're secured by this kind of collective agreement between multiple validators. And so if we take a simple case of a rule which says at least half of the validators have to be on a chain to make it valid, to make it acceptable, that means that it could also be undermined or mutated or retroactively changed if 51% or more of these whitelisted validators were to maliciously collude. And so it's true that private blockchains are not immutable, but they're not immutable in the same way that public blockchains are not immutable. There is a threat out there that could destroy them. And in this case, the threat is very different. The threat isn't about somebody rich buying a whole bunch of ASICs and doing a lot of hashing. The threat is about enough of the validators of that chain getting together and colluding in order to undermine the chain and obviously harm the interests, presumably, of the other parties that are participating in that chain. So it's a very different threat, but it's a threat nonetheless. And so I think the way to look at this is to say that, well, if you're a person that likes censorship-free money and doesn't trust banks or doesn't want to be dependent on banks and central governments, well, it makes fairly good sense for you to put your trust in the Bitcoin blockchain, because there's it's going to cost somebody a lot of money to undermine the system that you're using, and it makes sense for you to put your trust in that and to consider that immutable, even though someone could destroy it if they wanted to. And by the same token, if you're a collection of private entities who are able to identify each other and who have contracts with each other, it makes quite a lot of sense for you to trust each other in terms of not colluding to destroy the chain that you're all using together. Because if someone was to collude in that way, the evidence for that would be fairly clear. You'd have the old blockchain, the old fork, and the new fork, and you could prove in court that somebody had been getting up to no good. And it makes sense for you to be able to trust that kind of that group of validators working together, because you're able to take them to court if they do something wrong. So the use cases of public and private blockchains are very different, and the threat models to their immutability is very different, and the kind of people that would trust those types of immutability are very, very different. But I don't think it makes sense to have this black and white view that one is immutable and one isn't. So, blockchain number 3, tomato number 3, is the claim that this is not a blockchain, right? That we've described something which maybe is a new type of shared database. It's a valid type of system, but we shouldn't be calling it a blockchain. We should be calling it something else. So I want to kind of dive into this a little bit. So if you look at public versus private blockchains, there are a whole series of aspects of them which are different from each other, right? So for example, private blockchains have some kind of built-in permissions model: who can connect, who can mine, who can transact. Public blockchains don't have that. That means that private blockchains make it pretty easy to perform transaction censorship, to decide that certain types of transactions are not going to be allowed by the validators. In public blockchains, it's much harder to do that. They're not impossible, and we have seen examples of certain types of transactions being censored, but in a network with many, many miners in many different places with different interests, it's pretty hard to have a transaction censored in practice. Native cryptocurrencies are obviously crucial parts of public blockchains, but private blockchains don't use them at all. It makes sense in terms of public blockchains to talk of the blockchain. There is one, in the case of Bitcoin, there is one big blockchain out there, which is the blockchain, which has the most hashing power behind it, and which most people consider the leading blockchain, although Ethereum is now looking like a good second contender. But if we're talking about private blockchains, it doesn't make any sense to talk about the blockchain any more than it makes sense to talk about the website or the database. There'll be many, many different things owned by different people, and there's no one thing. And as we discussed, proof of work consensus plays a crucial role in public blockchains and not in private blockchains. So I will acknowledge that there's a whole bunch of ways in which public and private blockchains differ from each other. On the other side, there are a whole bunch of ways in which they're similar to each other as well. So, for example, they both have a peer-to-peer architecture. There may be more peers in a public blockchain than a private blockchain, though not necessarily. They both use Byzantine fault tolerance, meaning they're both designed around the idea that some nodes are able to malfunction, either maliciously or just technically malfunction, and then the network and the database is able to cope with that. They both use public key cryptography as a crucial part of controlling access to certain pieces of data. They both have the notion of transaction constraints, that are rules on which transactions are allowed and which ones aren't allowed. And they both generate consensus via a chain of blocks. So public blockchains and private blockchains, both by their nature, group transactions together in blocks, and then group those blocks together in a chain, and that's how they generate consensus between the nodes. And so if they both generate consensus via a chain of blocks, I think there's a case to be made that we can call them both blockchains because they have other similarities between them. But ultimately, I think we have to kind of defer to Ludwig Wittgenstein here, who says that when you're arguing about the meaning of a word, these arguments are a little bit pointless, because in practical terms, the meaning of a word is the way it's used in the language. And I think on that basis, it's fair to call these things blockchains, because people are calling them blockchains, and there's enough of a case to call them blockchains because they are similar enough to the archetypal Bitcoin blockchain. But if someone disagrees about this, then I don't think it's an argument that's so much worth having. If you want to call them shared ledgers or distributed ledgers or peer-to-peer databases or something else, then that's fine by me. But I think there's a reasonable case to be made that we can call these blockchains without trampling all over the English language and trampling over the differences between public and private blockchains. So I think that tomato can be dismissed on that basis. Tomato number 4 is that this is okay. We can call this a blockchain. It is a valid type of system, but there's no uses for this whatsoever. This actually has no use cases whatsoever. Public blockchains have some proven use cases, and private blockchains simply have no use. So let's talk about that tomato a little bit. So what are blockchains for, first of all, before I claim that they have specific use cases? Let's talk in a more general sort of sense. What are these types of blockchains for? So there's a very old problem. This old problem is some kind of shared database, or if we want to be more specific, a shared ledger, which has multiple writers, and those writers do not completely trust each other. So to take a classic example, your bank manages a shared database or shared ledger. It's shared in the sense that many, many different people are interacting with that ledger. It has many people who are writing to that ledger because each customer of that bank is generating transactions which are modifying that ledger. But those customers do not trust each other, right? I'm not willing for someone else who banks in the same bank as me to be able to take my money out or to do something with my account that I haven't given permission for. So that's a classic example of a shared database with multiple writers and limited trust. And the old classic solution to this problem is to create a centralized database at a trusted intermediary. So in the case of a bank, all the customers of a bank may not trust each other, but they have decided to trust that bank. And so they all use this shared ledger, the shared database, which the bank controls. They all interact with that database through the intermediary. And they all feel comfortable about doing this because they know that even though they don't trust each other, they're willing to trust the bank, that the bank isn't going to allow a transaction that they didn't approve, and the bank isn't going to steal their money. Although, of course, there have been occasions when banks have stolen money, but thankfully it's rare, and there are government guarantees in place to make it something which is very unlikely to affect most regular consumers. So that's the old solution to this problem of a shared database. And the way to look at a blockchain or a permissioned blockchain is that this is just a new possibility for solving this old problem. So you can solve it in the old way, with having a centralized database, but another way of enabling a shared database with multiple writers and limited trust is to use a blockchain. And this can solve many of the problems that the centralized database at an intermediary solves. It's just a new way of solving that same set of problems. So the way I like to look at blockchains is to look at them in terms of the trade-offs that they present vis-a-vis centralized databases. So any particular problem case which has a database behind it could be done on a centralized database, or it could be done on a blockchain. But there are advantages and disadvantages to these two approaches. And the key advantage of a blockchain, which we've already discussed, is this possibility of disintermediation, is the ability to have this database to be directly shared between multiple entities without a single entity being in charge of it, or without having to bring in some external entity to take responsibility for that database. And that's an advantage of blockchains, because disintermediation can lead to lower costs and less hassles and more simple processes. The key disadvantage of a blockchain, in comparison to a centralized database, is confidentiality. Confidentiality, not in terms of the whole world seeing what's going on in this database, like a public blockchain, but confidentiality in terms of all the participants in the database seeing all of the transactions that are going on. I'm going to put aside for now some of the advanced cryptography work that's going on in the space and which may well resolve this problem over time. But if you're looking at a blockchain for now and thinking about its advantages and disadvantages, this is an absolutely key disadvantage. And that is that every single node on the chain sees every single transaction. And it has to see every transaction because it has to verify every transaction for itself. And you can't verify something without seeing it. And that is very different from a centralized database in which the central authority that everyone trusts, they decide who gets to see what. No one can see the database directly. They only get to see what the central authority allows them to see. Whereas in a blockchain, every node contains a full copy of the database and is able to read everything, even if it's not able to write everything. Now, there are lesser advantages and disadvantages in terms of robustness and performance, which I don't want to get into, but some of my stuff online talks about those as well. So one use case of blockchain that many people got very excited about, and many people are still working on today, is the notion of post-trade settlement in the financial system. And the idea is that a number of banks would come up together to create a blockchain which would connect them together. Any asset can be issued onto the chain. So as we saw when we looked at the Bitcoin transaction, you can have multi-currency chains where multiple different types of assets are being transacted over the chain. So somebody comes along and issues an asset onto the chain, which represents dollars or pounds or shares or bonds or anything else. In this kind of system, we could do very rapid settlement because it's a blockchain, so all of the nodes are very rapidly synchronized. And within a few seconds, we can have a transaction which moves funds from one bank to another bank, and that transaction can be settled on the chain directly. It enables us to do safe, rapid delivery versus payment transactions. So for those of you who aren't familiar with the financial terminology of delivery versus payment, it's simply a safe swap of two assets. So again, to go back to the example we saw with Alice and Bob, when Alice and Bob swapped dollars for pounds, that swap took place in a single transaction. So there's no way that if for some reason something went wrong, either Alice or Bob could end up with both the dollars and the pounds. The transaction ensures that they both swap safely to each other, or if something goes wrong and the transaction never gets confirmed, they both get to keep their original assets. No one's going to be out of pocket. Because blockchains synchronize automatically, there's no need for reconciliation. So if you look at the financial system today, there's a whole load of reconciliation that goes on where constantly people are checking that what's in their databases matches what's in other people's databases, and this can be a slow and painful process, especially if there are some disagreements. And an added bonus of using a private blockchain for post-trade settlement is you can plug a regulator straight into the blockchain, give them a real-time read-only view of everything that's going on, and instead of regulators having to go and request reports from all the participants in the marketplace and then reconcile those reports and kind of match them and try and work out what's going on, the regulator can view in real time everything that's happening on that particular system, in that private blockchain, which means in that particular marketplace. So on the face of it, the use case of private blockchains for post-trade settlement looks very, very strong. And many companies went quite aggressively into this space. And our product, when we first started developing it, this was also the initial use case that we had in mind. And technically speaking, it's absolutely feasible, done and dusted, easy to do. You can do it on our platform today. You can do it on other platforms as well. There's only one problem. And that problem is confidentiality. And it's actually a huge problem. Because if you consider the idea of 10 banks setting up a blockchain to transact with each other, if 2 of those banks conduct a transaction, the other 8 banks are going to see that transaction because they're running blockchain nodes, they're viewing and verifying, validating transactions. And actually, that turns out to be a huge problem. It's a huge problem for 2 reasons. First of all, in terms of regulation, that is against many, many countries' regulation, that a financial transaction that takes place between 2 banks would be visible to parties that aren't related to that transaction at all. That's something which goes against a lot of financial regulation. And number 2, it's a competitive issue. If you think about, for example, competitive capital markets where banks are trading with each other, at high speed in a very competitive way, the last thing any bank wants to do is to have its full flow of transactions be visible to the other people it's trading with, in that marketplace. And things like, saying something like, well, they can just transact under many different addresses, or no one knows who that address belongs to, it doesn't really cut it, because as soon as you know something about your competitors from outside the chain, you can kind of correlate that with what they're doing on the chain. As soon as you transact with them directly, you can then watch where the money you send them goes later on, and you can learn about correlations between multiple addresses. And it can't really be solved in a simple way, this problem of confidentiality when using private blockchains for post-trade settlement. And so that use case, in my view, actually is a bit of a non-starter, even though it's something which many companies, started at least working on. So where do we see strong blockchain use cases? What I'm sharing here is not so much my kind of a priori opinion about where I think blockchains could be used. I'm actually just reflecting to you what people are doing on our platform, and things that people are building on our platform, and specifically focusing on the people that seem serious. When I say someone's serious, it means that they want to know about support contracts and they want to know about our roadmap, rather than people that are just downloading our software and kind of tinkering for fun. And if you look at those people and what they're building with private blockchains, you see really 3 or 3.5 use cases. Number one is what I call lightweight financial systems. Number 2 is provenance tracking. And number 3 is a more general inter-organizational record keeping. And kind of multi-party data aggregation is another way of looking at that, but when you have many organizations coming together on a blockchain. So those are the 3 use cases that we see people actually building on our platform today. So I'll talk a little bit about each of these. So lightweight finance. So first of all, as I mentioned, any asset can be tokenized on a blockchain. In other words, it is possible to take any kind of asset, be it financial or be it a home or a mortgage or a car, a gym membership. You can create a token on the blockchain which represents that asset. But what's happening in practice is that this token is being issued by some trusted entity. So someone comes along and says, I'm issuing a token in my name. What you're actually getting when you hold this token is a promise from me that you can return this token to me if you want at some time in the future, and I'll give you something real in exchange for it. So, for example, HSBC could issue dollar tokens on a blockchain. HSBC would essentially say, this dollar token you're holding represents a promise by HSBC to give you a real dollar if you give this token back to me. And presumably something of that nature would be valued by the market at $0.995 or something like that, because HSBC is very creditworthy. So you're not directly transacting in a cryptocurrency, but you're transacting in something which is issued by some trusted entity. Why is disintermediation of value here? Why is a blockchain of value here in comparison to a centralized database? Why is disintermediation a benefit? Well, the answer is that we can create more secure and cheaper systems using disintermediation. So rather than having a central authority which is in charge of the ledger, which keeps track of who owns what, and that central authority having to be trusted, having to be set up, having to be built up with employees, processes in place to prevent fraud, contracts, all of that stuff that you need if you have a central entity managing a financial system, you can get rid of all of that and have people transact with each other directly on a peer-to-peer basis if they use a blockchain. So that disintermediation has value in terms of simplifying the system and making it much cheaper. However, as we've discussed before in the context of an interbank settlement network, the problem of confidentiality limits the applications of this kind of system. And that's why I call this lightweight finance, because if you look at the applications that people are actually building on these type of systems, they're not stocks and bonds and cash. They are more lightweight things. So first of all, things like gift cards and loyalty points, these are more lightweight financial assets. First of all, because they're not regulated, or they're generally not regulated. And second of all, if you look at a gift card, in terms of the consumer, it represents a pretty small part of their overall financial activity. And in terms of the store which is accepting a gift card, it also represents a pretty small part of their overall financial activity. So even if we have a blockchain in which multiple stores get together to create some kind of gift card or loyalty point trading scheme, and they all see the transactions that each other are doing on this chain, and even if these stores are competitors with each other, they're not actually learning a great deal about what each other are up to, because they're only seeing a very small part of each other's transaction volume. And that's why blockchains seem to be a type of database which people are considering for this particular application. And kind of the flip side of that as well is that because the financial value of these systems is not that high, the idea of giving up that confidentiality for the sake of having a cheap and cheerful system that can be set up quickly and easily is something which needs to be a trade-off that people are willing to make. And the other thing we see as well sometimes, even in kind of more traditional financial areas, is if you have kind of a small trading circle. So if you have a small number of entities who want to transact and trade with each other, who aren't directly competitive, and want to just kind of set up some kind of cheap and easy system for doing that with each other without having to put someone, again, in charge of the database. So that's one use case that we see people building, on our platform, and I'm sure on other platforms as well. The second use case is called provenance tracking. So the problem of provenance tracking is the following. If you look at goods that move across a supply chain, from factories, say, in the Far East to consumers in the West, there are two problems in that supply chain that can be helped by this kind of system. The first problem is theft. People can steal goods on that supply chain, and they can still sell it on to the end user, and the end user doesn't really know that they're handling stolen goods, and the fact that they are might come back to bite them later on. So theft is one problem, and the second problem is faking goods or counterfeit goods, where someone comes along to create a good which looks like the original but isn't the original, manages to get their good into the supply chain, and the end retailer, the end customer, ends up buying something which is not from the original source and is either lower quality or doesn't have the same prestige because it doesn't have the badge of whichever label is meant to have manufactured that item. So provenance tracking is about trying to resolve those two problems, theft and counterfeiting. And the way in which you can do it is you can create a digital certificate of authenticity which is generated at the time when the physical good is manufactured, possibly even before that if it's licensed, but in the simple case when the good is manufactured. So a physical good is manufactured, at the same time a digital token is issued which represents the authentic source of that good. And every time that good changes hands across the supply chain, from distributor to shipper or to retailer, every time the physical good changes hands, this digital token, which represents authenticity, also has to change hands at the same time. And if you design a system like that, what you end up with is anybody who's holding a physical good also is holding a verifiable chain of custody, which enables them to convince themselves and prove to others that the good they're holding has a chain of custody going all the way back to the time of manufacture and to the place of manufacture. And that can solve both the problem of theft and the problem of counterfeiting. So why is disintermediation of value here? Well, with disintermediation, with using a blockchain rather than a centralized database, we can reduce the risk of fraud. Because as long as we have a centralized database, it's possible for whoever manages that database to modify entries or to do so in collusion with certain other participants in the supply chain. And the chain of custody can be relatively easily corrupted compared to a decentralized system in which no individual actor or no small group of individual actors is able to corrupt that chain of custody. And that's something which is of value to us. In terms of confidentiality, as I'll show on the next slide, because of the flow of transactions in this type of system, we can achieve a lot of confidentiality by using multiple addresses. We have fewer transactions between competitors. Depending on the particular use case, regulation may or may not be a concern, but if regulation isn't a concern, we can use the fact that the flow of transactions is much simpler in a supply chain compared to a financial marketplace to achieve confidentiality or sufficient confidentiality, even while we use this kind of shared peer-to-peer database. And this kind of demonstrates the idea. So if we look at the way that assets move around in a financial marketplace, we might have 5 banks that are trading with each other, and assets will be bouncing between them back and forth all day long. So banks, even though they're competing with each other, are also transacting directly with each other, and over time they can build up a pretty detailed profile about what everyone is up to by watching what happens to the transactions that leave them, go to someone else, and then come back to them, and then leave them again and come back to them again. Assets go back and forth many, many times. If you look at a supply chain, the flow of these transactions, which would represent the chain of custody, is much more linear. Manufacturers have no reason to hand off goods to each other. Manufacturers hand off to shippers, shippers to distributors, distributors to retailers. And at no point in this system do we have any reason for people that are competing with each other to transact with each other. They're just handing off to the next level in the system. And as a result, there's much less that the participants in a blockchain can learn about each other if the pattern of transactions is linear in this way than in a kind of financial marketplace. And that's what makes the confidentiality problem less of an issue for supply chains than it is for financial marketplaces. The third use case that we're seeing people build on our product is just more general inter-organizational record keeping. So the idea here is a number of organizations want to come together to collectively record and notarize something. And these things that they're notarizing and recording could be anything. It could be communications, it could be financial transactions, it could be just some kind of documentation that they exchange with each other. It doesn't really matter from a technical perspective. What's happening technically is that digital signatures are being used to annotate the origin of each item in this database. So people are claiming ownership of the authorship of certain pieces of data in the database. And then we use the properties of immutability to ensure that once some data goes into this database, it cannot be retroactively modified. So what we have here is a number of organizations that come together to create a shared archive in which each piece of information in the archive has a known origin and cannot be retroactively modified. And as I mentioned before, you can look at this either as a way to prevent disputes between a small number of organizations, or you can also look at this as a convenient infrastructural solution for a situation where many organizations or many small entities are all writing to a database simultaneously, and they can do that in a peer-to-peer way rather than having to put that database under someone's external control. So why is disintermediation of value here? Well, like before, we remove the need for a central party or an external party who's in control of this. So you could create an internal organizational record by having some central party which is sent data by each of the participants. It then creates the authoritative database that contains all that data, and then it transmits that database to everybody. You could have things working in that way, but that means you're going to have to trust that central party, and that means you have to set it up, and you have to have people there and processes and contracts and all these other things. If you can do this in a direct peer-to-peer way between the participants, then we have a cheaper and simpler system. They're able to build this collective record together directly rather than having to put their trust in someone external. And confidentiality isn't really an issue here. Well, first of all, the whole idea of this system is for the information that goes into it to be visible to everybody. So confidentiality doesn't really rear its head. But if we want confidentiality in terms of having certain pieces of data only be visible to certain participants, well, we can just use regular encryption to do that, or we can use hashing or digital fingerprints, which is a kind of simpler way to understand the notion of a hash. So we don't have to put the actual original unencrypted data in the chain. We can put encrypted data in the chain where only certain people have the key to unencrypt it, or we can put a hash of the data in the chain, in which case maybe only the author has the original data, but they can reveal it later if they want to. And whatever method we use, we still gain this property of immutability, and of those who need to know being able to see and be proven to that data was added to the chain at a certain point in time. So confidentiality is simply not an issue here, because the whole idea of this kind of system is to have at least something which is visible to all the parties in the chain, even if that something is encrypted. So those are some of the use cases that we're seeing. So here we move on to tomato number 5. And tomato number 5 is, this is all great. You know, it has some, let's say it has some use cases, but it's actually, this is nothing new. And actually, I think that tomato hits home quite fairly. Because if you actually look around, there have been companies building systems like this for a while. The one I know best is a company called Gideon, based in London. There's also another company called GuardTime who've been building these sorts of systems for a while. They were building these systems before they were called blockchains, but the characteristics of these systems are exactly the same as the characteristics of permissioned blockchains. So you have multiple authors, you have transactions batched into blocks, you have digital signatures on those transactions, digital signatures on the blocks which confirm those transactions. You have some kind of distributed consensus scheme, and you ensure that all the nodes are in agreement with each other. And actually, systems of this variety have been built for quite a while, and at least a couple of decades when I say quite a while. So it's fair to say, I think, that permissioned blockchains are not as new as people like to make out. However, I think there are some aspects of them which are new, as far as I know. First of all, the Bitcoin transactional model, in which the inputs of one transaction are connected to the outputs of previous transactions. As far as I know, combining that type of transactional model with this kind of immutable database is a new combination, and it's a very powerful combination, because what the Bitcoin transaction model enables is instant duplicate detection. So you don't have to wait for the system to reach consensus in order to know that two transactions are conflicting with each other, because that means that two transactions are spending the same output of a previous transaction. And this is a very powerful thing. I've written about this, I won't go into detail, but you can actually look at the Bitcoin transaction model as a distributed version of multi-version concurrency control, which is a popular method of concurrency control in regular centralized databases. I think it's a very powerful paradigm. It enables us to do all sorts of things on these blockchains that previous systems didn't enable. The other thing which I think is new, as far as I know, is Ethereum's notion of representing the entire state of a system in a single hash. And that's, for those of you familiar with Ethereum, that's the state root. State root is the root of a very big, again, I'm talking a little bit technically here, a very big Merkle tree. What the state root essentially does is express in a single 32-byte number, a unique fingerprint of the content of the entire state of the Ethereum database, such that if you were to modify any small part of that database, then the root would change. But that any hash can do. What the root does, which is much more powerful than that, is it represents that content in a way which enables a very compact proof to be presented of any single part of that database. So given a particular state root, which two parties agree on, one party can prove to another party the state of a particular aspect of a particular contract in the Ethereum blockchain in a very, very efficient way without having to reproduce all of the data in the chain, just having to reproduce a small number of points on a tree which lead to a leaf which contains that data. So I think that's a very powerful thing, and it enables all sorts of models of how these systems can be interacted with that weren't enabled before. So I think that is something else which as far as I know, is new in this type of system. But I think really the thing which is newest is the fact that there's a huge amount of awareness now. So, pardon me, everyone's talking about blockchains. Even Hillary Clinton, I'm not sure she has such a clear idea of their use cases, but I think some have more. People are talking about blockchains. We have also productization, which is very important. So these types of systems that people were building before were always built bespoke for a particular customer in a particular way. And now we've got platforms coming out whose aim is to kind of make this stuff easy to do out of the box. So Ethereum is a public blockchain, but it's also a code base that can be run in a private way to create private blockchains, which have, kind of enable all of Ethereum's functionality. MultiChain is our own product, which is quite popular. Hyperledger project, which is a kind of a joint open source project between many different participants in the space. Again, their aim is to create a product. We have Tendermint, which is more like a software library which can be used for generating these types of systems. We have the R3 consortium, who actually seem to have, to a significant extent, moved away from blockchains, but still have a blockchain as part of their solution in the Corda product they're developing. And you have the Eris platform, which is kind of a developer toolkit to make it easy to build blockchain solutions of all sorts of types. So we have productization going on, and that's not something that was there before. And as soon as you have productization, what that means is the cost of developing a particular application of these types of systems drops dramatically. Because instead of having to write the whole thing from scratch or do custom adaptation of a particular code base, you can use an off-the-shelf platform like Ethereum or like MultiChain, build your application on top of it, and you're running just as efficiently as you would be if you were building an application on top of a centralized database. And so that's something which is going to enable many more of these types of applications to be built, because the cost of doing so will be much less. Tomato number 6 is that blockchains are overhyped. So obviously there's been a huge amount of hype about them, and this tomato would say, well, they've been overhyped. And I'll just let you, can you see the cartoon there? So I'll just let you spend a minute or two looking at these cartoons, which I have to say I took from elsewhere, and you've got the URLs there. And at least one of these was actually adapted from a cartoon that came out around 20 years ago, which was written about relational databases, which at the time were the big hype and the big excitement. And kind of this is an adapted blockchain version of the same thing. But I think if you consider how much people talk about blockchains and these type of cartoons, which obviously represent reality in some way, I think it's fair to say that actually that tomato hits home. And I think it's fair to say that these are overhyped. Blockchains have been assigned roles from saving the whales to enabling hunger to be ended in Africa and all sorts of things like that. And I think that's a little bit ridiculous. I think this is a useful new type of database, which can make some things efficient for some companies and some sectors. It may be a very important new type of database, but I don't think it's going to be any more important than something like NoSQL databases. I find it very difficult to imagine that this is going to be anything bigger than the NoSQL movement, which if you're an application developer is absolutely huge. But nonetheless, I don't think it's fair to say that NoSQL has transformed the world in terms of governance structures and how governments work and how people interact with each other. They're simply a very useful tool in the IT toolkit, and I think it's fair to say that private blockchains could be something similar. And the last tomato, which I've heard said quite often, is that this is all vaporware. So we all know about public blockchains. We use them; they work, but there's no private blockchains out there. So this is my opportunity to somewhat plug our own product. So MultiChain is available now. It's an off-the-shelf platform for creating private blockchains. We've aimed to make it really, really easy to set them up and to deploy them. So our model in terms of designing the product is something like MySQL in terms of ease of use. Integrated permission management, so you have all sorts of control about the different types of things that people can do, who can connect, who can transact, who can issue assets, who can generate blocks, etc. It has native support for assets as well. So for those of you familiar with colored coins, what we've done is we've taken something a bit like colored coins, but brought it down to the network level. So rather than it being a protocol which is grafted on top, and which isn't understood by the nodes of the network, we have multi-currency support at the network level, and every node is tracking the issuance and the movement of the exchange of every single type of asset. And that lets us do all sorts of powerful things that you can't do with colored coins. And it's very, very extendable. So right now you can have up to 8 megabyte of data attached to any transaction, so you can embed any type of data you want inside the blockchain. In the next few weeks, we'll be releasing a version with a completely rewritten wallet, which will make this much, much more practical in terms of scalability. And then I assume that 8 megabyte limit will go up quite a lot further. So you can use MultiChain to have assets which are transacted and exchanged, but you can also simply use it as an immutable data store for any type of information that you want to store securely between multiple parties, which cannot be retroactively changed. Just to give you a sense of kind of what's going on in the market, so this shows the number of people that came to the MultiChain website through search, organic search, that's not paid search, month to month. So you can see here there's been quite a rapid growth in terms of acquisition of traffic to our site. This reflects a combination of the popularity of our product and also of the rapidly growing interest in the whole idea of private permission blockchain. So compared to a year ago when we first released the product, just at the end of June 2015, we released the product, there's been really quite a dramatic growth in interest in this field. And I think we need to treat this with a bit of caution, because I think some of the use cases that people are talking about aren't valid, and so we may even see this go down at some point. And then kind of grow again in a more long-term sort of way once kind of the genuine use cases are focused upon. And for those of you familiar with the Gartner hype cycle, it might well end up looking similar to that curve. So that's my kind of talk for the evening. I'm very happy to take any questions. If you go to the MultiChain website, you can download some stuff, see the Get Us Started guide. There's a whole bunch of developer documentation, and that's one of the places where I publish my blog, where I talk about all sorts of aspects of private blockchains, generally not specific to our products at all, so that might be of interest to some of you. So thank you very much for listening, and I'll be happy to take any questions.
So my question is, I'm really interested in the way you can have a private blockchain.
You see there's been quite a rapid growth.
Oh. You still there?
Yeah, I'm still.
Yeah. I'm not sure, it just popped across. Okay, sorry.
So I'm interested in the way that you can have a private blockchain and actually specify who mines. In particular, what I'd like to know is how you're able to, if you like, grow the network, add extra peers to the network, and advertise to those peers who, which miners or which keys, or public keys, if you like, are allowed to sign new blocks.
Could you hear that?
Mostly, but repeating would be helpful.
I don't know how to summarise that. So basically, it's to do with. Do you want to just stand up?
Yeah.
To do with how miners are chosen.
Yeah, so I'm really interested in private blockchains, in particular a way you can essentially scale the network, so add new clients, but still keep a limit on who's allowed to mine in new blocks with a private key. Do you use like central authority to distribute who can do that, or how do you go about that?
Yeah, so great question, thank you. So there's many different ways. So I can talk about how our product does it. So our product, when the chain is generated, the creator of the Genesis block gets permission to do everything. We have all sorts of different types of things that are permission. And then one of the permissions is the administrative permission, and that is an entity which can control the permission of other entities. So this node which generates the blockchain can then add other administrators, and simply adding an administrator means that it assigns the administrative permission to other public addresses. Then there are rules in the chain which you can customize, which say for what type of changes, how percentage of the administrators have to agree on it. So for example, once you have 10 administrators who've been given permission in the chain to be administrators, it might be that to add another administrator, at least 8 of those 10 have to agree. And that's how you can generate kind of collective administration from an initial kind of seed, you create a group of administrators and they can collectively administer the chain. So that's part of the answer. Another part of the answer is that for each of the types of permissions that a chain has in multi-chain, you can make that permission free for all. So you can, for example, have a chain which is free for everybody to connect to, everyone to send, everyone to receive, but is permissioned in terms of who can validate blocks and who can administer the network. And in that way, you can have a kind of, some people call this a hybrid blockchain, where it's permission for some things and not permission for other things. So you can do that as well. I think you asked in your original question about how the chain can be discovered. So what we do in MultiChain is each node has what's called a node address, which is a combination of the chain's name, the IP address of the node, and the port, the TCP/IP port on which that node can connect to. And that's kind of summarized in a single string, which you can essentially publish, and then other people can just kind of download MultiChain and very easily connect to that endpoint. And then if it's an open chain, then they can connect straight away. And if it's a closed chain, they get then shown their public address, which they then need to get sent to administrator who will give them permission to connect. So it's fairly easy to take care of all of these things in a pretty practical way.
Okay, brilliant. Thanks, Gideon. Would you mind going full screen with your face, just because it's very small?
No problem.
Or at least on our screen it's very small. I'm sure it's not the size. Cool. So, next question. There was a couple of hands up. Do you want to just come up and ask it? It's probably easier than...
Yeah.
Okay.
Hi Gideon, thanks very much. So I'm a PhD student looking at some of these possibly overhyped environmental and social use cases for sort of blockchain technology, private and public. Have you come across any of these, and what do you think of them?
Yeah, so public and private, first of all, I think you have to treat public and private very differently. I think public blockchains, the key feature of public blockchains is censorship-free transactions. And I think that really is quite a new thing. It has all sorts of bad use cases, like terrorists sending money across the world, or ransomware, which I think is a very strong use case of Bitcoin today, and it has all sorts of positive use cases in terms of enabling financial inclusion. So somewhere, anywhere in the world, someone anywhere in the world can download an app to their phone, and suddenly they can send and receive money with other people in the world without having to be approved by any kind of bank or any kind of financial institution. And that's a very powerful thing. I think right now it's overhyped for that use case because the capacity of the network is very, very low in terms of the transaction volume. But I can certainly see a way in which over the next 5 to 10 years that capacity grows by leaps and bounds to the point where actually it is quite a practical, high-volume transacting network, and then that will be a genuine use case as financial inclusion. If we talk about private blockchains, I just don't see them as a socially transformative technology. I see them as a way for companies to make the way in which they work with each other more efficient. But it's still those companies, they're still in charge of the database together. It's really just a replacement for having one of those companies in charge of the system. So yeah, they'll save some money, they'll save some hassle, but I find it hard to see how it's socially transformative.
So in terms of things like identification, property rights, that kind of thing? Yeah,
so property rights, I mean, I don't envisage a situation in which anyone is going to put their home on a public blockchain. In other words, the idea that if someone steals, your mobile device and your laptop, and you've got two-factor authentication to a multi-sig, that they can take ownership of your home in any meaningful legal way, I can't see that being practical. I can't see people really having really important pieces of property on a public blockchain. In terms of identity, yeah, I think people talk a lot about the identity on a blockchain. I think a blockchain could be a very suitable way for example, many banks to collectively manage identity rather than each bank managing identity on its own today. I think that is a very reasonable use case for blockchains in terms of an interbank identity database. But again, that's not transformative, right? That's just about kind of making it easier for you to share your identity in multiple places.
Okay. Brilliant. Anyone else before I go back to Alan? Alan?
Right, quicker one this time. So I'd be really interested in a smart contract that could store and access its own cryptographic key material. That way you can get true escrow, say by a contract, i.e. money transfer wouldn't have to be triggered by an event, they could do it themselves. I spoke to some of the Ethereum guys when they were last down. They said they were interested in it but couldn't do it. Has that changed?
I don't know enough about the particulars of this. Is this because you have a particular idea about how the scheme should be developed, or you just hope to see it develop?
So it's something I've thought about it, but I do think I do think it's hard to achieve or impossible to achieve, but it's something very desirable.
Yeah, so putting aside zero-knowledge proofs and that kind of area of cryptography, which is very interesting, but still kind of somewhat in the lab, you can't really have confidential information on a blockchain because, let's say this private blockchain had some way of storing its own key. And at some point, some transaction triggered it using that key, making a signature with that key. Well, the code that's being executed to do that, at some point has to see the key. So even if the key isn't visible, in plain text on the blockchain, each node at some point is going to have that key in its memory, because without that key, it can't generate the signature. And that means that anyone who modifies the code of their node to stick in some debugging information, a bit like view source in a web browser, they will then have access to the key. So, things of that nature, you're going to have to use, very advanced kind of zero-knowledge cryptography where the transaction can be signed and verified without anyone ever seeing the private key in the first place. And I don't know enough about that type of system, and I'm not sure that it's mature enough to make this practical for now, but perhaps in future.
Okay. Anybody else got any other questions? No? Okay. Okay, so one quick question from me, just to bring it all down to something very simple. From your perception and view on private blockchains and everything else, what do you see Bitcoin actually doing? I.e., is it just going to be something that's tootling along in the background that's not particularly useful? Is it going to be, is it going to have a far more use over a long period, or is it just going to be replaced by other systems? So once we start looking at public blockchains.
Yeah, so I guess unusually for someone working in private blockchains, I actually do think that Bitcoin will be around for the long term. I think if you look at the graph of transaction volume, it is growing quite consistently, and obviously a lot of that is speculation, but I don't think all of it is. I think the idea of a censorship-free currency, or if you like a digital gold, or however else you want to describe it, I think it is quite powerful and quite compelling, and I see Bitcoin being around in the long term, primarily as a currency, or a store of value, a way for people to transact. I also see a lot of value in having a blockchain in which people can embed small pieces of data which then become immutable. So to go back to something that I was talking about in the context of private blockchains, you can summarize a large piece of data in a hash, which commits that piece of data to certain content without revealing that content. You can then stick that hash in the Bitcoin blockchain. It then over time becomes secured by an immense amount of computational power. And what that actually lets you do is prove that a certain piece of data existed at a certain point in time, 5 years or 10 years later. So I think Bitcoin itself as a currency has applications, and I think the Bitcoin blockchain as a place to store other pieces of data also has applications. So I'm long on Bitcoin, and I've purchased Bitcoin in the past, and I'm planning to hold it for the long term. Ethereum is very interesting because it's much more powerful than Bitcoin. Obviously, it's taken a bit of a hit in terms of what happened with the dead hour. But just to clarify the comment that you started at the beginning when I said that Bitcoin was like a toddler being forced to cook Ethereum was like a toddler being forced to cook dinner. What I was just saying is that I think Ethereum is really still quite young and immature at this point, and it's actually a bit of a problem that it has to hold so much market value that it currently holds, because I think it could do with a couple more years of maturing before it got that big. So Ethereum is also very interesting as a cryptocurrency. I don't see it supplanting Bitcoin because it's less well suited than Bitcoin for being a basic cryptocurrency and less well suited for basic data storage. But if we do find some strong use cases for smart contracts in public blockchains, which we may do, I think also Ethereum is likely to be around in the long run, or something like Ethereum if they can't get the technical issues solved in Ethereum itself.
Brilliant. Okay, thanks very much. Does anybody else have any other questions, or is that? Okay, I think that's us then. Thank you very much, Gideon. Where can people reach you online? Just through Twitter, through your website, your blogs? Those are the best places?
Yes, if you go to MultiChain.com, there's a contact form there, there's a Q&A, there's a link to Twitter, all of those places.
Excellent. Okay, well thank you very much for joining us, and we'll just thank Gideon in the usual way. Thank you very much.
Enjoy your meeting.
So just a couple of things to touch on. Video, thank you very much to Product Forge who are videoing this and streaming it live. We're going to get the video out. The last video is live. It's accessible online now. I'm not sure how long that will be, but it will hopefully be before the next meetup, certainly. I'll share that on Twitter. I should share that on the Meetup site as well, so if you haven't signed up, that's the best place to get it. Thank you very much. Again, goes to Deloitte Digital for paying for the room, paying for the drinks. We're going to drink the drinks now, those that are left. The next meetup is the final thing, Tuesday, August the 2nd. We don't have a speaker confirmed yet, but I've nearly got it confirmed, and I think hopefully it will be an in-person speaker. We shall see. If it is, he's fantastic. We just need to get a few things agreed first. And that'd be awesome. If not, then he will be Skyping in, or somebody else. So please do sign up and try to get people interested in learning more about this. Does anybody have anything to say or to share in terms of blockchain stuff that you're working on that you need to speak to somebody else about at this particular point in time, or do you just want to do it over drinks? Okay, drinks it is. Thanks very much for coming. Cheers, everybody. Thank you.